you think about a very basic exponential, y is equals to e power x. Let's take that. Let's start off very simple. Now, the first thing you should be thinking about, and what you generally should be thinking about whenever you're sketching a particular graph or a particular function, is the intercepts. In this particular case, the y-intercept, which again is where x is equals to 0, the y-intercept will be 1, because e power 0 is 1, right? Anything raised to the power 0 is 1. Your x-intercept is going to be a little more trickier in this particular case. Well, it's trickier to spell as well, right? Because the issue here is, if you do equate, let's say, y as 0, how do you normally find your x-intercept? You equate y to you take y 0, and then you solve for x. You can't really do so, because if you take y to be 0, then you have to apply ln on both sides, and that's just going to give you a math error. Because the idea here is that your exponential graph never touches your x-axis. It gets very, very close to it, but it never really touches it. So you can't really ever plot a particular x-intercept. However, you do definitely know it's going to pass through, it's going to cut your y-axis at the value of 1. So what happens is, it starts off as you have negative values of x. Obviously, it's very, the y value is very small, and this really good, just really, really close to your what do you call it, to your x-axis. It never touches it though, so I can even write never touches x-axis, although it gets very, very close to it. Obviously, the more negative the value of x, the closer you get to your x-axis. It comes here, it cuts your y-axis at 1, and then it increases at an increasing rate. That's the basic idea behind your exponential function. Again, it will never become vertical. However, as you increase the value you're putting of x, the y value will just keep increasing at an increasing rate. So this really becomes, well, if I can just draw the final result here, something along these lines. This is your y is equals to e power x. This would be 1, right? So if you think about it now, in fact, I think I can just make it on this particular diagram. Now, this was y is equals to e power x. If you think about y is equals to, I'll draw this in green, e power 2x. The intercept here, again, you won't have any x-intercepts, but I mean, you can't define them at least. But the y-intercept here would still be 1, because if x is 0, e raised to the power 2 into 0 would still give e power 0, which is still 1. So it should still pass through this particular point, right? It should still cut the y-axis where y is 1 and x is 0. However, if you think about it, if you have something raised to the power 2x as compared to something raised to the power x, if, let's say, this point was, I don't know, I'm sticking a random arbitrary point. Let's say this point was 4, where if you have e to the power 2x, it should obviously be a point above this, right? Because, well, if you're raising, it's being raised to a higher value, a higher power rather. Well, that wasn't supposed to happen. No worries. Even if you look at it like this, like, let's say this point here on your on your e power x curve, if you take e power 2x, because it's being raised to the power 2x rather than just x, whatever value comes about should obviously be higher than the original curve. That's the basic idea here. So as a consequence, this does pass through this particular point, but it increases at an even faster rate. Well, it doesn't completely go vertical, you can't show that, but yeah, it'll definitely be above your e power x curve, and here it still won't touch the x-axis, but it'll be below. That's the idea. This is e power 2x. If you wanted to draw e power half x, for example, that kind of follows your same idea, where a half x should basically still cut through here, but be below e power x at all points where x is positive, giving you something along these lines. Well, kind of got messy to as I went to your negative x's, but something like this. This is easier to visualize if you just put in a few values of x. So just try to calculate y for, let's say, x is 1, x is 5, x is 10. It becomes easier to figure that out with these three different functions. But I'm just going to give you this basic concept, and I think that should be enough. So there you have it for your for one case of exponentials. Let's look at another case though. Look at another basic case to start off with, where it's y is equals to minus x. Now, if you remember, which you should because I just drew it, this was y is equals to e power x. Y is equals to e power minus x should also cut at the point where y is 1, because again, if you input x is 0, you still get 1. Because e power minus 0 is still going to be 1. However, the idea here is it kind of reflects one. Well, one could say it kind of reflects with your y-axis, giving you something of this sort. And if you input values of x into these particular functions, it becomes easy to understand. But this should be enough to give you the basic idea, which is all you're going to need in your paper. So if I can draw some of these, or I could even just draw them on that particular diagram. We saw that this is e power 2x. Again, it shouldn't touch the x-axis, but my drawing isn't the best, so like, please excuse me. And this should be e power minus, well, my apologies. Wait. It should be above the curve of e power minus x, so something like this. And again, it shouldn't touch the x-axis, but my bad drawing. And likewise, we saw e power half x lies below e power x, giving you something of this sort. This is e power half x. Let me get rid of this. Right, and just using that, if e power half x lies below e power x, then e power minus half x should lie below e power minus x. It goes without saying, giving you something of this sort. This is e power minus half. Whoops. Yeah, so maybe got a little messy, but hopefully the idea is now clear behind your exponential of x and of e power minus x. We can look at another thing here, which is interesting. So let's just go back and draw our basic exponential e power x. Sorry, there's no negative here. So this is e power x. Now, what if I asked you to draw minus e power x? Now, if you think about this, this is really just e power x, and every single value of y will just be multiplied by a minus sign. So let's say if here the value of y was 4, you would want minus 4. If here it was, let's say, 8, then you would want minus 8. If here, let's say, if it was 1, then you would want minus 1, giving you this exponential curve. This is e power minus x. Sorry, no, not minus x. Very sleepy today. Minus e power x, right? And you can do this for e power minus x as well. If you have, this was e power minus x, and hence this would be minus e power minus x. Okay, so there's just one last thing left to cover in exponentials. Okay, so the last thing I want to cover about exponentials in this video is what happens when they're multiplied by something, by a particular number, let's say 2, 3, 4, whatever. and what happens when something is added to it. So like, what if your function was something along these lines? Now, again, I will continuously keep drawing your basic exponential just so that we have something to compare, right? And this is obviously 1. Now, if you have, let's say, the exponential of, let's take this as 2e power x. Now, if you try to figure out the y-intercept here, which is what happens when x is 0, this would give you something along these lines. This is 0, which gives you 1, so 2, right? Meaning, in this particular case, it would cut your y-axis at a different value, and if you try to draw it, the idea here, well, it's not supposed to go completely vertical, my bad drawing on my part, but the idea here that this is more steep than your e power x, because it's being multiplied by 2. Every value of y is being multiplied by 2. This is what we're drawing. Anyhow, right? And if you also try to figure out the range of values for which this particular exponential is valid, we can do that as well. Okay, so range of values, and as you can tell, I've tried to redraw the new exponential to make it look a little prettier, but I don't think that worked. Anyhow, so the range of values, if you think about it, your exponential is valid as long as it doesn't touch your x-axis. So means for e power x, it has to be greater than 0. I mean, because e power x is basically y, right? Is the y value. So whatever value, whatever output you're getting from e power x, it has to be greater than 0. It can't be equal to 0, because that would mean something, that would mean touching the x-axis, like here. It always has to be like in places that are greater than 0. So if you have 2 e power x, as you can see in this case, it shouldn't have any difference. If you take the 2, you divide it over there, giving you e power x greater than 0. So even 2 e power x should still be greater than 0. It will still have the same range of values. The reason I'm mentioning this is because it's not going to be the same for our next case and our final case for exponentials, where if you look at what happens when something adds to them. So this is your basic exponential, and I think I'm getting better at drawing them. Please say yes. Anyways, and what happens when you want to draw e power x plus 1, let's say. Now, if you want to figure out the y-intercept here, you can note that this will have a change. Why is that? Because x is equal to 0, you put it in, that gives you 1 plus 1, that gives you 2. So it's going to be cutting your y-axis here. And if you really think about it, every single value, let's say if this, whatever value this was, let's say this was 3, this is going to be 4. This was like 8, this is going to be 9. Every single value is going to increase by 1. So this curve is going to be translated upwards by 1. It's basically going to be a shift upwards. So what you can see, something along the okay, bad curve alert, something like this. So it's going to be like basically every single value. Well, this stuff should have gone here. So every single value is just going to be increasing by 1. So it's just going to be kind of like a completely upward translation. Now, the only thing interesting here is if you really look at the range of values here. Let me use a different color for that. Let me use green. So for e power x, it was valid if this was greater than 0. If e power x, you're adding 1, then this should be, just to balance, you should add 1 on the other side as well, right? So this should be valid if it is greater than 1, which is what you should see here. So like if we take this greater than 1, if I just draw a line here, think of the line y is equals to 1 to be your new x-axis, in fact. So here, this particular exponential will get closer to the line y is equals to 1, will never touch the line y is equals to 1. because whatever is happening with e power x will be happening with e power x plus 1, just an increase of 1, a shift of 1, a translation of 1 upwards, and that concludes our graphs for exponential.